So let's start from there as a starting point and then come to the idea of the instantaneous velocity as we go through. And then by the end of the lesson, you will not only understand what the instantaneous velocity is, you'll know how to visualize it on a graph, you'll know how to calculate it using the derivative and the concept of a limit in calculus, and then we'll apply it to several problems. And so by the end of it, it'll be crystal clear exactly what the instantaneous velocity actually means. And so let's get started. So from the last lesson, we have learned what the idea of the average velocity is. And we said the average velocity was equal to delta x over delta t. And if you remember, delta x is just the final position minus the initial position, and then the time is the final time minus the initial time. Now, the whole thing about this is that basically we have to have 2 points on the curve, right? So one point at time 1 and another point at time 2. And all we care about is how far did the thing travel, the distance, and how long did that take? Distance divided by time, very simple. And it's the average velocity between these points in time that we're actually calculating. Now what I'm going to do is I'm going to give you the punchline for the instantaneous velocity right now, and then we're going to talk about why it makes sense. We're going to spend the whole lesson understanding what I'm about to write on the board. Instantaneous velocity. Instantaneous velocity. Now, instead of 2 points in time where we're trying to find the average velocity between, like here, what we're interested in physics is understanding what is the instantaneous velocity right at that moment in time. Imagine a rocket launching. The rocket raises up off the launch pad, is going very slow. If you could take a very small snapshot in time at an instant, its velocity would be small. But then 5 minutes later, if you could take an instantaneous snapshot of its velocity as it's launched 5 minutes into the future, it would be very fast. And once it's in orbit, if you could take an instantaneous velocity at a moment in time, when it's in orbit, it's even faster. It's really, really fast, right? We know the velocity is increasing. We can, of course, take an average between 2 points, but what we want to do is instead of looking at 2 points far apart and finding the average velocity, we want to bring the 2 points closer and closer and closer together so that we actually find the velocity at an instant. We call it the instantaneous velocity. Now, what the instantaneous velocity is mathematically is v. Notice we don't put average anymore because this is not an average. And it's the velocity is equal to, we'll talk about this in a minute, it's the limit as delta t approaches 0. This means delta t approaches 0. And it's delta x divided by delta t. Notice it's the same exact equation, delta x over delta t. The only thing we've added is that now we take the limit as delta t goes to 0. Now, we're going to draw a lot of pictures, but visually, in the past, we took 2 points in time and we calculated an average velocity. It was basically the slope of the line that connects through the 2 points that we're interested in. But now what we're going to do is we're going to bring those moments in time closer and closer together, and we're going to continue calculating the velocity between the 2 points. And as we use the power of calculus to bring the 2 points of time closer and closer so they're basically on top of each other, or infinitesimally close to each other, basically like 1 point in time. That is the idea called taking the limit of something as the time interval approaches 0. So we're still taking the distance and dividing by the time between 2 points, but we just bring those 2 points basically so they're infinitesimally on top of each other. That's what this is called. Now, in the language of calculus, when you take the limit of something, delta x over delta t as delta t goes to 0, we have a special word for this, and this is called the derivative of x with respect to time. So when you see dx divided by dt or dx dt, it means the change in x divided by the change in time, but when we put the d's here instead of the deltas, the d's mean that we have shrunk everything down so that we're no longer separated very far. We shrink them down, and when you take calculus, you understand the exact way in which we do that and the theory behind it and all that. But I'm just telling you that fundamentally that's what you're doing. You're starting separated, and you're finding delta x over delta t. Once we shrink it down to the point where they're basically the 2 points are on top of each other, then we no longer call it delta x anymore or delta t. We call it dx dt. This means incredibly small distance. This means incredibly small time interval. We divide them, we get the velocity at an instant because the 2 points were basically brought together. So this is so important that I'm going to circle it because this is the fundamental idea of this lesson. All right. Now the rest of the lesson is I want to prove graphically to you that this is true. And then what we're going to do is do a quick example at the end to show you how the derivative works with the velocity and so on. But in words, if I wanted you to remember one thing about this lesson, this would be it. The velocity is the derivative of the position. I'm going to say it again. The velocity of a particle is the derivative, which is the rate of change of the position with respect to time. The derivative of the position. The velocity is the derivative of the position. The velocity is the derivative of the position. Say it again and again, because that is always true. You'll learn it in calculus, you'll learn it in physics, and you will use it throughout your entire career, learning anything in physics, engineering, math. It's just never going to go away. The velocity is the derivative of the position. The derivative of the position we're always talking about with respect to time, of course. All right, so let's talk about this for a second. Let's go over here and just draw a picture. Now my pictures, I'm going to have to draw several of them in sequence. And as much as I try, they're never going to be exact. So just kind of give me a little forgiveness here and imagine that as I draw them, I'm doing my best to keep them consistent. But I'm not going to be able to be exact. So here's the time and the position in meters, time in seconds, exactly as we have drawn it in the last lesson. So I'm just going to draw some tick marks. I'm going to try to draw them consistent, but I'm not going to be able to be exactly consistent. 1, 2, 3, 4, 5. I'll take this one off just to make it easy for me. And then what I want to do is draw the position of some particle with respect to, or as it compares to, or as a function of its time. So what I'm going to do is start right here, and I'm going to go up, and then I'm going to bend over something like this. Now I'm going to try to draw this red curve over and over and over again, as many times as I can, but I'm never going to be able to draw it exact. So if it doesn't look exactly like this in the next drawing, please forgive me a little. It's supposed to be exact, right? Now, before we do anything, let's talk about what we learned in the last lesson, and let's also just think about it a little bit. This means that the position starts at -5 meters, 5 meters to the left of the origin, because you got to turn your head sideways. Remember, this is 0, this is negative distance, and this is positive distance. This is +5, right? And basically it starts really not moving, but then it rapidly starts moving because in this region, it's traveling at a very high rate of speed. It's traveling a large distance in a short time. Think about between this second and this second, it traveled all the way up to here. And then it's traveling and traveling and traveling. This is a very high rate of speed, but over here, it's traveling at a very low rate of speed, right? And the way you know that is because, look at, if you kind of pick 2 seconds here, it doesn't travel very, because this is the distance over here. It doesn't go very far up. So it's not covering very much distance in 1 second, whereas here, it's covering a very large distance. So clearly, the velocity is not the same at every point in this curve. The velocity starts small, it's going fast, and then it starts to bend over and taper off, and it's not traveling very fast up here. But what if we want to calculate the instantaneous velocity at this point in time right here? So I'm going to put a number 1 indicating this is where I want to know the instantaneous velocity right here, at this point, right there. Not over here, not over here, not down here, right there. We know that it's going fast here and it's going slower here, so it has to be slowing down as it passes through point number 1. We don't know what that number is, but we know it has to be slowing down. Here's what you do. Instead of trying to worry about calculating its velocity there, what you do instead is you pick some point far away over here and put another point here and call it point number 2. And you find the average velocity between points 1 and 2. We did this a few lessons ago. I drew almost this exact same picture. So how do you find the average velocity between 2 points? Well, all you do is graphically what you're doing is you're connecting a line which goes through these 2 points right here. So it's the dashed blue line right here. And the slope, we said that we talked about it, the slope of this line is the average velocity between points 1 and 2. And so the average velocity between points 1 and 2 is delta x over delta t, right? And what we do is we say that that's x2 minus x1 over t2 minus t1. All right? So all we do is we literally look at point 2, we find its x position. We look at point 1, find its x position. We subtract them, that goes in the numerator. And then here, this is like, I don't know, it's 8 or 9 seconds, whatever it is here. And then t1 is like 5 seconds or something over here. We subtract the times. So we have the distance traveled between point 1 and 2, because remember, it's on this axis. The time traveled, or the time elapsed, and then boom, we get meters per second. And what we talked about in a few lessons ago is that this is literally the same thing as calculating the slope of the line that connects point 1 and point 2. Because the slope is rise over run. And what you've done by calculating delta x, because this is the x-axis, is you found the rise between these 2 points. That's the rise. This is the rise. And the run is the time elapsed. So by calculating delta x dividing by delta t, you have literally calculated rise over run of the line that connects those points. So we connected this in the last lesson. We said the average velocity was just the slope of the line connecting any 2 points on the graph. All right, now this is the average velocity here. What we really want is the instantaneous velocity here. So what we're going to do in the next drawing is we're going to bring this point a little bit closer. Let's bring it somewhere around right there. So let's redraw the graph over here. All right, and again, I'm sorry ahead of time, it's not going to be perfect. Even the XY axis here is not the same. So I'll put T, this is seconds, X, this is in meters. I'll put some tick marks. Something like this, 1, 2, 3, 4. I know I start the graph down here at -5, so I'm trying to be consistent about there. So here's -5, here's +5, 1, 2, 3, 4, 5. And the rest I don't really care about. I'm going to start here, and it's going to go something like this. It goes something like this, and it bends over. All right, is it exact? No, but it's supposed to be pretty close to exact. Point number 1 is somewhere over here. Point number 1 is somewhere over here. So I'm going to put a dot right here, and I'm going to put point number 1. All right, so now what we're going to do to try to get closer to, see, this is a good approximation of the velocity here, but it's not so great because point number 2 is far away. Let's bring point number 2 closer, and then we should get a better approximation of the velocity at point number 1. So what we'll do is we'll bring point number 2 to about here. Now there's point number 2. All we did was bring it closer. So we literally could do this. We could literally just calculate the slope of the line connecting these 2 points like this. So what I'll do is hopefully not mess it up, and I'll draw a line connecting these 2 points right here. How do we find the average velocity in this case? We're just going to say the same thing. Average velocity is equal to delta x over delta t. Same exact equation as before. How would we do it in practice? We find what is the x position here? Okay, it's about 5. What is the x position here? That's the initial. It's about, 3.5 or something like that. What is the time elapsed? I don't know, it's about 2 seconds. You can read it off the graph. You'll divide them, and you're going to get a new velocity. And that new velocity will be the average velocity between these 2 points, which would be the slope of the dotted blue line. So you see what happens. As you have a point far away, you have an average velocity, which is the slope of this line. It's an okay approximation for the instantaneous velocity here, but it's not so great because point 2 is far away. Look at all the changing happening between point 1 and 2. But if I bring this thing closer, then suddenly this approximation is a lot better for the instantaneous velocity here because, of course, point 2 is closer. And the slope of this line is a better approximation to what is going on locally around point number 1. Can you guess what's going to happen next? So I will say that over here, I'm going to say this is an okay approximation for the instantaneous velocity here. This, I'm going to say this is a better approximation for what is going on here. Can you guess what I'm going to do next? I'm going to take point number 2, I'm going to bring it infinitesimally close. See, in the next drawing, I would draw it right next door. Like literally where it was almost on top of it. But what I'm going to really do in the next is I'm going to bring it almost directly on top of this next guy. So let's go down over here to the next drawing. And let's say this is t in seconds. And let's say this is x in meters. And we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Just do a few tick marks. So it doesn't really matter, but I know that I start my graph every time here. And I know I try to break it something like this. All right, is it exact? No, it's not exact, but you get the idea. So point number 1 is right around here. I'm going to put point number 1 right here. So what happens is originally point number 2 was over here. I found the slope of the line connecting. And then I brought point number 2 here. I find the slope of the line connecting. Then I bring the point closer. I find the slope of the line connecting. Then I bring point number 2 0.00001 seconds into the future. And then I bring it 0.00001 seconds in the future so that it's basically right on top of it to the point where now I'm going to circle it and say that essentially I have a second point so close to it that you can't even tell that it's a different point. And then essentially we say that we have taken the limit of this delta x over delta t, which is the slope of the line between the points, but we brought the delta t to 0. Because here's the delta t here, the delta time is like 5 or 6 seconds, right? The delta t here is about 2 seconds. You could bring the delta t half a second. What about a microsecond? What about a nanosecond? You bring it so close together, it's right on top. Then, instead of the slope of the line connecting 2 separate points, what you have here is like the slope of a line which is tangent, we call it tangent to this curve. It only touches this curve in like one little place right here. And that it only, when we say a line is tangent to a curve, we mean that it just kisses the curve. It touches it only in one place. Instead of going to 2 separate points, when you bring the points close together, it just touches the surface only at point number 1. All right? And then, so we're going to call this the tangent line. And just like the slope of this was the average velocity, the slope of the tangent line is what we call the instantaneous velocity at that point. And then we say that the instantaneous velocity is equal to the limit of delta t approaching 0 of delta x over delta t. And in calculus, we rename this whole limit process and of all this stuff as just dx dt. All right? So the bottom line is, when I told you, and I repeated like 16 times, I told you that the velocity was the derivative of the position function, right? The derivative with respect to time. And I tried to get you to memorize that by saying it over and over again. Literally what I'm saying is, if you know the position of a function and you take its derivative with respect to time, then you get a new function called the velocity. Now, calculus goes through the details of what you're doing here and drawing the pictures and so on, and calculus provides you the rules on how to take derivatives. See, but what the derivative is, when you look at the definition of the derivative in a calculus class, which you can look at my classes if you want, all it is finding the slope of a line as those points get closer together. And the limiting process is called the derivative. And you're given a bunch of rules for how to take derivatives of functions, right? You're taught how do you take the derivative of a polynomial. You're taught that. You're taught how to take the derivative of 2 things multiplied together. You're told how do you take the derivative of 2 things divided by each other. You're told how do you take the derivative of an exponential. You're told how to take derivatives of logarithms. You're taught how to take derivatives of sine and cosine and tangent and all the other trig functions. So that is really half of Calculus 1, how to take derivatives. Now you can see why it's so important to know derivatives. Because I'm telling you that if you know the position of a particle, x, and you take its derivative, you have a thing called a velocity. So if you observe a particle in a laboratory making some path, and if you could take that path and map it as a function, a position function, and then calculate its derivative using the tools of calculus, then you immediately know its velocity everywhere at all points. And the velocity will be the slope of the line tangent at that point. So this is point number 1. The slope of the line tangent is called the velocity, right? Now, over here, what is the tangent line going to look like over here? It's going to be shallower, almost 0. So it has a lower velocity here, right? The slope is in the middle here, so it's a middle velocity. What is the slope of the line tangent to a curve here? The slope of the line would be something approaching like this, a very high slope. And then down here, notice the curve bends a little bit. The slope here is very, very low. So what you have here, you have a low velocity, very high velocity, lower velocity, and a velocity approaching 0 again. So by looking at the slope of the curve as it moves, you know intuitively what the velocity of the particle should be doing. It's the slope there. And to show you that a little bit more directly, I'm going to draw you another example of a different curve here. Let's say we observe something in the laboratory. All right, so here is t in seconds, and here is x in meters. And what I'm going to do is I'm going to say we have observed some particle doing some motion like this. First, it goes up, and it does something like this. Now you got to be careful when you look at this thing, because this is the time axis. What it really is going on is the particle starts out in a negative position, and then as time goes on, it gets closer to 0, and then it gets to a maximum distance, and then when it's going down over here, it's really backtracking. So it's like on a number line, here's 0. The particle starts here, then it goes here, then it turns around and it goes back, and then it turns around again. That's what's happening. So it's like going to positive x, then it's going down, then it's turning around. So if you want to just look at the motion on this, it's like going up and then down and then up again like this. So it's not that it's doing a real roller coaster path in space, because one of these axes is time. It's a one-dimensional motion. It's going and then turning around and it's going back like this. That's what's happening, right? But we can still tell what the velocity is right here. What is the velocity at this point? Is it high or low? Right, at point number 1. Well, the tangent line, this is a position curve. So the velocity is the slope of the line tangent. So I'm going to mess this up, but I'm going to try to draw something like this. The slope of the line tangent is very high and it's positive. So the velocity is positive. Right? The velocity is positive right there. What is the velocity of the particle right here? Well, this is right at the tippy top where it turns around. So actually the tangent line is totally flat right here. What is the slope of a flat line? The slope of a flat line is 0. So right here, the velocity is exactly equal to 0. Same thing is going on down here, because the tangent line right here is also flat. And so right here, the velocity is equal to 0 again, right? Because why? Because remember what's happening. The particle is starting to the left of 0, that's down here negative. It's going here and then it has to turn around. But as it turns around, its velocity has to become 0 for just a moment. I mean, you think about it. If this is the particle, if I'm going to turn around, then I must stop momentarily to come back. At that moment of stopping, the velocity is 0. These are the points when I'm turning around. The slope is 0, and that means the velocity of the particle is 0 because I'm turning around. Now over here, the slope of the tangent line is again positive, so the velocity is greater than 0, again positive. What is the slope right here? Well, it's hard for me to draw right here without cramping it, but the slope of the tangent line is going to look something like this. So the slope is negative right here. So the velocity here is less than 0. The velocity is negative, right? Now, what does that mean, by the way? So here we have, this is really what's happening. These are positive numbers, a position here. These are positive here, like +1, 2, 3, and this is -1, 2, 3. So this is like -3 right here. So when I have a positive velocity, it means I'm moving in the x direction. When I have a negative velocity, it means I'm moving towards the negative direction. So when I am here, I'm traveling towards the positive x direction, so my velocity is positive. Here my velocity is 0, I turn around. As I'm traveling down, my velocity is negative because I'm traveling towards the negative x direction here. Then, once again, I turn around. So the speed is 0 for a second, the velocity. And then as I move again, my velocity is positive. So at any point on this graph, at any point on the blue graph, if you can see what the slope of it is, you can tell if the velocity is positive or negative or 0. And because that is the slope of the line tangent, which we also call the derivative, if you calculate the derivative of the position function, you know the velocity at any of these points. And I'm going to show you that in just a minute with a very good example. But before we get to that point, I want to talk to you about the instantaneous speed. Instantaneous, that's what that means, speed, right, is equal to the magnitude or the absolute value of the velocity. Notice that I said sometimes the velocity is 0, sometimes the velocity is positive, sometimes the velocity is negative. So we said velocity has a sign. The sign tells you which way it's going. So velocity is a vector because it carries direction information, positive or negative, and it also carries a number, how fast the thing is going. But speed is basically like how fast you're going. It doesn't even matter what direction you're going. So you take the absolute value. The velocity might be 0, it might be positive, or it might be negative. If we take the absolute value, we strip away the sign information. The instantaneous speed is simply the velocity number with no sign information. So we just take the absolute value of this guy. So the title of the lesson is Instantaneous Velocity and Instantaneous Speed. If you ever need to know the instantaneous speed, you just find the velocity and you take away any sign information, take its absolute value, and you have the instantaneous speed. All right? Now, what we want to do is put this into practice. We're going to do a great many problems, okay, to get you comfortable with this. But I want to do one really quick one right here to drill it down. We've said many times that the velocity of a particle is the derivative of the position, which is the rate of change of its position with respect to time. And we use the tools of calculus to find that derivative and so on. What we want to do here is do a concrete example. Let's say that I have a particle, and I'm going to draw what that particle looks like, right? I'm going to draw it on this little grid right here. And this is x. And it's going to be a different graph than what I've drawn before, so I won't bore you with exactly the same situation or setup. So let's say that it looks like a parabola. So for here, it goes like this. Something like this. And what I'm going to do is I'm going to draw the back end of it, but I'm going to draw it as a dotted line. Because really, we only care about the motion of this thing from time 0 on. We don't really care about the negative time before the experiment starts, but it's the mirror image, and you can see it's not even a perfect parabola. But you get the idea. This is a nice parabola, okay? And what I'm going to tell you ahead of time, I'm going to tell you that this particle, x, this is in meters. This is not a function of m. This is just telling you meters. X of t, I'm going to tell you, is t squared. So now what I've done is something different than the previous problems. I've drawn a path. I'm telling you what the function of the position is, and it is a function of time. That means what you do is you literally measure a particle. At every second, you measure its distance away from the origin. And you put all that, and when you graph it, you find out that it's an exact parabola. What would something like this look like? Right? We can make a little chart. We can say this is t, and then we can find x of t, which is equal to t squared. So I'm telling you now, I'm not just drawing a picture. I'm saying here's some measured data. So what we basically have figured out is that, remember, this is one-dimensional motion. So at 0 seconds, 0 squared is 0, so it's 0 meters away from the origin. Right, it's right there. Then at 1 second into the future, we square the 1. That 1 squared is 1, and so x is equal to 1 meter away. All right, now 2 seconds, we put 2 in there. 2 squared is 4, so we are now 4 meters away. At 3 seconds, 3 squared is 9, we are now 9 meters away. At 4 seconds into the future, 4 squared is 16, we are now 16 meters away. And I'll do the last one, 5. At 5 squared, we are now 25 meters away. All right? So this is an example of an actual function. You might actually be in the lab on one-dimensional motion, and you might literally start your clock, and you might say, okay, at 0 seconds, where am I? I'm at 0. At 1 second, where am I? Well, I'm 1 second, I'm 1 meter away. At 2 seconds, I'm now 4 meters away. At 3 seconds, I'm now 9 meters away from the origin. At 4 meters, I'm now 16 meters away from the origin. And I write all this stuff down. I put it into a chart, and I realize that this is exactly a parabola. So the position of this thing is really a function of time, and it matches exactly a parabola. So if you graph it as a function of time, it draws this beautiful parabola shape. Now, before we do anything with calculus, tell me, right here at the origin, is the velocity low or high? Well, right here at the origin, the slope of the line tangent is flat, so the velocity is 0 here. But right here, the slope of the line tangent is positive, so this is a positive velocity. But the slope of the line tangent here is much, much higher, so it's a higher positive velocity. So what this is telling us is we start at 0 speed, then we have middle speed, higher, 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 higher speed, because the tangent line is increasing its slope all the time, because velocity is the slope of the line tangent to the position curve. Does it make sense? Does this map something that looks like it's speeding up? Well, look, in 1 second, I only went 1 meter. But over here, in 1 second, I went a ton more meters. I have to be traveling faster here. So as I go through this motion, even from the raw position data, it looks like the thing is speeding up. And from the graph, we can tell that the velocity is constantly increasing. So now, let's apply what we've learned in this lesson, which is the main thing we've learned in this lesson is to find the velocity of anything. Once we know its position, we just take its derivative with respect to time, and then we have a new function called the velocity, and that velocity will tell us the velocity of the particle everywhere after we do this. So what we do is we say, all right, what we'll do is we'll go over here is we will say that the velocity is equal to dx dt. But x is equal to this, right? So x is equal to t squared, right? So what we do is we take the derivative of this function, which is t squared. So I guess you could plug it in. You could say you could do t squared, but that's too complicated. Basically, let's just erase this. That's kind of silly. We know how to take derivatives of polynomials in calculus. When you take the derivative of this thing, the derivative of t squared, you pull the exponent down, and you put the variable there, and then the exponent becomes the original exponent minus 1. So the derivative of t squared is 2t. If you don't know how to do that, then you really just have to review the calculus. That's covered in the very beginning. We learned very, very early on how to take derivatives of polynomials. So any polynomial you give me, I can take the derivative. The exponent comes down in front, the variable is here, and then the exponent is minus 1. So 2 minus 1 is 1. So the derivative here is 2 times t. All right? So what we figured out is that the velocity as a function of time is equal to a new function here. And I can put any time I want into this thing, and I can calculate the velocity of this particle anywhere. So let's go ahead and do it by putting it into a table here. So we can put the same times in, and we can say that the velocity is equal to 2 times t, 2 times time. So let's do something similar. All right, at time 0, what is the velocity? Well, I put 0 in here, and the velocity is 0 meters per second. This is in now meters per second, right? What about at 1 second? I put 1 second in here, and the velocity is 2 meters per second. At 3 seconds, or in the future, the velocity, 2 times 3, is 6 meters per second. Look, the speed is increasing, right? And I skipped one because I can't even count. Apologize for that. So let me go and fix that. 2 seconds in the future, 2 times 2 is 4 meters a second. 3 seconds, 3 times 2 is 6 meters per second. 4 seconds, 4 times 2 is 8 meters per second. And at 5 seconds, 2 times 5 is 10 meters per second. Look what's going on. As the time is increasing, the velocity is increasing. These are all in meters per second. Every one of these things, meters per second, meters per second, meters per second. This is telling me that this thing is speeding up to a maximum of 10 meters per second or right here at t is equal to 5 seconds. All right? And that's exactly what we said, because when we look at the original graph, look at time is equal to 0. We predict the velocity to be 0, but look at time is 0. The tangent line, I'll draw it right underneath, is exactly flat. The slope of the line tangent is 0. That's why the velocity is 0. At 1 second, which is, I don't know, you could put a little dot right there if you want to, then we have the slope of this line right here, which is 2. With the slope of this, I don't have my drawing exactly right, but the slope of this is higher than 0, right? And when you get way over here toward the end, what you have is the slope of the line tangent of a very, very steep line, and that is why. So that's why the velocity increases. So here the slope is 0, so the velocity is 0. Here the slope is a little bit bigger, so the velocity is bigger. And then the velocity is bigger and bigger and bigger because the slope of every one of these tangent lines gets bigger and bigger and bigger and bigger as we go. I'm going to draw one more graph, and then this lesson will be over. So just stick with me all the way to the end here. So in the top here, we drew the position of this particle as a function of time. Now let's plot its velocity as a function of time. We just said the velocity is 2 times t. And we know how to, we can draw some tick marks if you want, but we basically know, I'm not going to try to make this thing accurate, but we know that a slope of 1 is something like this. This is a line with slope 2, so it has to be a little steeper. So it's going to basically be something like this. It's going to be a line that goes more or less something like this. Because the slope is 2, right? Rise 2 and run of 1, something like this. So what we have figured out is that the position of the particle looks something like this. The velocity of the particle is a line. What this means is that 1 second, the velocity is here. 2 seconds, the velocity is here. 3 seconds, the velocity is higher. 4 seconds, the velocity is higher. But at every moment of time that I'm increasing the speed, I'm speeding up at the same rate. I mean, I'm always going faster, but every second in the future, I'm increasing my speed at the same rate. Now, very soon, we're going to talk about the acceleration. When we increase our speed, we call it acceleration. And so I'm accelerating at a constant rate because every second I'm increasing my velocity by the same amount. You can see it's increasing by 2 every time I go up here. All right, I think that is enough. The point of this lesson is to show you what the instantaneous velocity is, which is what we've been doing up here, to prove to you why it's the derivative of the position, and then to show you a quick example. And we're going to do more examples in the future with with example problems in just a minute. But just to recall, in the beginning, we talked about the average velocity, delta x over delta t, between 2 points in time. And we picked those 2 points in time anywhere we want, and we basically said that when we find delta x over delta t, we're finding rise over run. So we're finding the slope of the line that connects these two, right? And if we want to know the velocity at exactly this moment, we'll just bring point number 2 a little closer and find a new approximation. So we bring it a little closer, we find a new line that goes through both of these points. The slope of this line is the average velocity here, which is a better approximation than the one we had before, but it's still not great. Let's bring it right on top, infinitesimally close. So we say that it's now, those 2 points are not separated anymore. Really, they're right, very, very close to each other. So the line that was connecting them is really what we call tangent. It touches the curve at one point. And the velocity of the particle at this point is the slope of the line tangent to that point. And we say that the instantaneous velocity is the limit of delta x over delta t as the time interval gets very, very small. We call that in calculus the derivative of the position as a function of time. Now, in real life, we usually model the position as a function. And so we can then take the derivative of that and we can find the velocity anywhere we want. And we kind of gave another example and said, what about a different motion of a particle? Sometimes the slope of the tangent line is positive. Sometimes the slope of the tangent line is negative. Sometimes the slope of the tangent line is 0. When the slope of the tangent line is 0, that means the velocity is momentarily 0 as the particle turns around. Here the particle is moving positively. Here the particle is moving negatively, meaning down towards negative. And here the particles are turning around, right? And the instantaneous speed is just the instantaneous velocity when you strip off any sign. That's what we call speed. And then we said, all right, let's do an actual example. Now we have a particle we've measured in the laboratory, and we collected data. At every second in time, this is the distance the particle is away from the origin. That is mapped exactly into a parabola. You put the value of the time in, and it comes out with the distance away that it is. And from the tools of calculus, we can then take the derivative of this thing, of this function. X is a function of time, and when we do this, it becomes 2t, and then whenever we get that, we can plot this guy, and we know then its velocity at any point in time. And we can just see that the thing is speeding up the whole way, which maps exactly with what we say here. The slope is 0, then bigger, 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 so it has to be speeding up. When we plot the velocity, we get a totally different curve, but basically these are lined up such that this curve is telling you the slope of the line tangent at any point in time, and you can see that the velocity is increasing as time goes on because the slope of all the lines tangent is increasing as time goes on. I'm repeating myself several times as we go through it because I believe it's necessary. If you got it, I'm super happy. But most of us, it takes a little while to internalize. And you have to cross-reference. The slope of this thing, the slope of the line tangent, that's the velocity. Okay, I plot the velocity. Okay, it's going up. Okay, it's positive. It's negative. It's 0. What does it mean? You got to think about this stuff. You can't just like, oh, I got it. You move. I mean, I think you have to, it needs to bake in the oven a little bit, right? And the stuff we're learning here, you learn it in calculus in a little more detail, a little more rigorously. But what we're going to do now is use this information to conquer some problems in physics dealing with the instantaneous velocity. So if I want to know the instantaneous velocity of a particle at any moment in time, what I do is I take the derivative of the position function, and then I put in that value of time, and I will get a velocity at a specific instant of time. And so then as that rocket raises off the ground, it's going very slow, but the rocket then goes faster and faster, and I can find the instantaneous velocity as I move on into the future by taking the derivative and putting in any value of time that I want. So go through this a few times, follow me on to the next lesson. We'll solve a few problems with instantaneous velocity. Learn anything at mathandscience.com.